Welcome to the new version of graph theory. Today we are going to be talking about the specific problem of vertex coloring, also more generally just referred to as graph coloring. So consider it's some application where we have some number of units of work that we need to do. Represented here by a bunch of vertices within our network. So there's some dependencies between these tasks. Remember when we talked about directed acyclic graphs, that there might be some kind of dependency in terms of one task needs to be finished before another task completes. Here we're instead considering kind of the related problem where an edge between two separate units of work, two tasks that we need to do, represents that these two tasks can't be done at the same time. Maybe there's some kind of data dependency between them or something else along those lines. So we have some kind of, set of relationships between our, as we see here, our 5 different tasks. So these two tasks can't be completed at the same time. These two can't be completed at the same time. That's essentially what we're representing right here. So if we want to complete all these tasks, say in parallel, and avoid any of the data conditions or race conditions that might arise based off of these dependencies here, we want to figure out how quickly we can do it in terms of the number of steps that we need to do. So at our first step, we can complete some number of tasks that are an independent set from the rest of the tasks in our network. Next step, we can compute essentially on some other independent set of tasks. And so essentially the problem is trying to find some minimum number of independent sets within our network so we complete our full set of tasks in the shortest amount of time in terms of the number of time steps we have to do to complete whatever we're working. So, naively, we can kind of come up with some labeling in terms of at each step what tasks we can in fact complete at that specific step. So, the vertices labeled as 1 are tasks that we can complete time step 1. Obviously, they are independent from each other. They're an independent set within our graph. Likewise, step 2 and 3 we can complete as its neighbors are in task 1 and task 2. This is essentially the vertex coloring problem. It's essentially identifying some vertices within the graph that are an independent set and labeling every single vertex to be in some independent set. So we talked about coloring specifically, but generally speaking, just for ease of drawing it out and everything, we're going to be labeling vertices not with explicit colors, more so just with some number. And again, this is reducing essentially to just identifying some number of independent sets. So obviously, like we talked about naively, we can do that as each individual vertex can be placed within its own independent set. So for a graph on n vertices, we can have n independent sets, and that would be a coloring of our graph. So the vertex coloring specifically we can consider as some function or some mapping or some labeling of all vertices within our graph to some labeling contained within S, where the possible colors are, as we're using numeric identifiers for colors within our graph, are going to be 1, 2, 3, ... up to some possible k. So the number of possible different unique labels we can have on our graph is just going to be Okay, so every single vertex is going to be labeled with some 1, 2, 3, dot, 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 up to k. All right, so as we've seen so far, we haven't really restricted yet, per our definition, the possible colors we could give to each vertex within a graph. We just said it's some kind of mapping, vertex to color, vertex to label. Specifically, since that's not particularly an interesting problem, because we could just naively color each vertex with color 1, each with color 2, etc., dot, 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 up to, all vertices being colored with color K. So we want to consider the more interesting problem, which is essentially what we're going to be considering from here on out, is a proper coloring. This would also be referred to as a valid coloring, or any number of names, valid graph coloring, valid vertex coloring, or, as we're going to define right here, a proper coloring. So if we have for all vertices within our vertex set to some label, we'll define our coloring as this L of V, where L of V is within our S, as we defined before. A proper coloring, our coloring here, all vertices labeled with some color, is going to be proper if we consider for all edges UV within the edge set of our graph, labeling of U, the color of U, is not equal to the color or the labeling of V. So again, proper coloring, if we consider for all vertices within our graph, we have some color assigned to them within some S, which we'll get to in a second, based off how we defined it before. So again, proper coloring is, we consider all vertices within our graph, each with some label, some proper. So proper coloring, if we consider for all vertices within our graph, each assigns some specific color. A proper coloring is if we consider any two adjacent vertices within our graph, they have different colors. That gives us specifically a proper coloring of our graph. So going back to our motivating application, we had that graph defining those, let's say, data dependencies within our parallel application. We essentially came up with a proper coloring like we had before. Had labeling for each vertex to say we could process these two vertices at the same time, these two vertices at the same time, this vertex separately without having to worry about those data dependencies. So similarly here, this is a proper coloring. If we evaluate based off of our definition from before, each edge within this graph, we see that the endpoints of that edge all have a separate color. Now, if we would say make a change here, change this label to 2, this would no longer be a proper coloring, because if we look at this edge specifically, or this edge, we see that the endpoints are the same, so it invalidates the definition that we had before. Conversely, let's consider relabeling this vertex now to 4, this vertex now to 5. This would be a proper coloring because if we consider each individual edge, we consider the endpoints of that edge, they have separate colorings. So, naively, we could just color each vertex in our graph with a different color and we have a proper coloring. But, that's not really, again, an interesting problem because naively we have the solution that's proper coloring, it's valid coloring for any possible arbitrary graph we can come up with. So specifically, I'll touch on this. So specifically, let's note the fact that for our coloring to be proper based off of our definition, it doesn't matter how many multi-edges we might have in our graph, but any self-loop immediately is invalid. In terms of no graph can be properly colored if we consider, just going by our definition before, a graph with self-loops, because both endpoints of the self-loop are that same vertex. So the whole point here is, generally speaking, the graphs we're going to be considering for the next few lectures are going to be, generally speaking, I mean, just for simplicity, we'll consider them as simple graphs, although as we saw here, multi-edges don't really matter because these two edges, based off of our definition from before, would evaluate in the same way. So either both endpoints are different colors, and per this edge, this is a proper coloring, or both vertices have the same color, so it's no longer a proper coloring. So going back to considering the fact that we can naively color each vertex with a separate color within our graph, that's not an interesting problem. Generally, what we are going to be focusing on and talking a lot about is what we'll term as the minimal vertex coloring problem. Essentially, that's finding some proper coloring of our graph that has a minimal number of colors. So again, going back to our motivating example, when we were considering that the amount of time it takes to complete our application based off these task dependencies, a minimum number of steps essentially is the quickest we want to finish our application. So it takes 3 steps, and like this graph here, we have 3 separate colors. For a minimal, really minimum, so the minimum vertex coloring problem, as we just defined, is a proper coloring of some graph G that has minimum number of unique colors. So the minimum vertex coloring problem is essentially identifying such a possible coloring for our graph G. And generally speaking, let's say minimum number of unique colors, which we'll define as K. So generally speaking, we're trying to both identify what this K is, as well as actually determine what the specific coloring is that will give us that specific K. So this problem, like a lot of the problems we talked about, is generally a very difficult problem to solve computationally. So generally speaking, we cannot get some proper coloring of any non-trivial graph exactly. But what we can do is come up with some certain bounds. So the second half of class, essentially, that's what we'll be doing. So talking about the minimum vertex coloring, talking about our K, which is the minimum number of colors we need to color a graph. That's also referred to as the chromatic number. So we generally write that chi of G, which equals sum K, as the minimum number of colors to properly color our graph G. So chi of G, which we'll say equals some arbitrary K, is the minimum number of colors we need to properly color some graph G. So if we say the chromatic number of our graph is 3, that says there exists some proper coloring of our graph that requires some k equal to 3 possible colors. So that other graph that we saw before, that we used in our examples, this graph here, the question is it possible, what's the minimum vertex coloring we can have on this specific graph? If you think back to bipartite graphs, we know that they can be separated into 2 independent sets, 2 bipartite sets. So going off what we've talked about here, minimum vertex coloring, chromatic number, or proper coloring, and their equivalents kind of to this independent set problem. Bipartite graph can be colored with 2 specific colors. Is this graph bipartite? We can see it has an odd cycle, so obviously it is not. If we consider that triangle specifically, since every vertex is attached to every vertex within that specific click subgraph, each of those vertices must have some unique color. So we'll get to that in a second in terms of saying, for clicks contained within a graph, how that affects our possible lower bound. But in this example specifically, we had change the colors slightly, but 2, 2, 1, 1, 3 is a proper coloring of our graph. So in this specific example, we can't, as we've seen, color this graph with 2 colors, but we can color it with 3. So the chromatic number of this graph is going to be 3. So again, in a little bit, we'll talk more about the bound specifically on the chromatic number of any arbitrary graph. So there's one more thing I want to touch on, and that's the notion of color critical graphs. So a graph is color critical if for any possible subgraph H, the chromatic number of that graph H, that subgraph H is less than the chromatic number of our full graph G. So H is a subgraph of G, except for the subgraph H that's isomorphic to G. Remember when we talked about subgraphs, technically a subgraph containing all vertices, all edges of our full graph is a subgraph of that graph. So here essentially what we're saying is H is a subgraph of G, H is not isomorphic to G, so all possible subgraphs of G except for that subgraph that's isomorphic to G itself. Essentially what this means is that if we remove any single edge or any single vertex from our G, we end up with a graph that has a lesser chromatic number. So G here, if this holds, G would be a color critical graph. And the reason why I wanted to bring this up specifically now is just kind of introduce this notion of criticality, because we're going to talk about it later on in a variety of different topics in terms of different properties for graphs that we'll consider, where we have some X critical graph. So here specifically that X is referring to color critical, or color being, the chromatic number of our graph. So essentially, as we'll also talk about later in the course, if we remove any vertex, any edge from our graph, we end up with some graph with a property that's different than the graph itself, generally referring to that X here, in this instance being the chromatic number of our graph. So considering back to our original example, the question we might have, is this a color critical graph? So our proper coloring, our proper original coloring. So we have our proper coloring, a proper k equals 3 coloring here. By this definition, in order for this to be a color critical graph, if we remove any single edge, any single vertex, we'll end up with a graph with a lesser chromatic number. So let's consider removing that specific edge. And it looks like Doesn't really change much in terms of the minimum number of colors we can color this graph with. It's still not by part type. It still has this 3-click, so it still requires at least 3 colors. So chromatic number of our subgraph here in this instance still has the same chromatic number as our original graph. So this would be, in fact, not a color critical graph. But if we say consider that subgraph of our K3 specifically, if we consider, say, removing any arbitrary edge, so without loss of generality, since it's a click, we can just select any edge arbitrarily, remove it. We can recolor our graph with 2 colors now. And if we would consider, say, specifically removing any arbitrary vertex, obviously we'd be removing multiple edges, at least in this connected graph. The subgraph that results can also be colored in fewer colors. So our original triangle, our original K3, would be, per our definition, a color critical graph.